Okay, this video is going to cover L'Hopital's rule for limits. So we're going to talk about limits for a little while again. So go ahead and put that in your table of contents. Standard L2, this is page 112. These are the pages that you got yesterday in class. So if you didn't get them, there's more in my black box by where everybody picks up their papers for those that were absent. Okay, so the target is student will apply L'Hopital's rule to indeterminate forms using the derivative process to determine the limit of a function. So when we started limits, we started with limits that look like the two at the top. Now, we learned how to solve limits a couple of ways. We learned that algebraically, we could do things like direct substitution. So that was always our first step for every limit, was direct substitution. Sorry, this is terrible writing. Let me rewrite that again. So we had direct substitution, which is where we always started. That didn't work. We had things like factor and cancel. We had rationalization. We had simplification of fractions. And then for limits to infinity, we had our three rules, whether it was top heavy, bottom heavy, or equal. That kind of helped us break it down. We looked at always which was growing faster. Growing faster on the top, that means our limit went to infinity. If it was faster on the bottom, that means our limit went to 0. If they were the same, it was just ratio of those leading coefficients. Okay. So we always started with the direct substitution. So if we look at those two specific limits at the top, and we do direct substitution for our C values. The first limit, our C value here, remember your C value is that value right there, the value we're approaching. If we plug in to the top, we get 0. If we plug into the bottom, we get 0 again. Okay, and we knew that was a problem. So we do something like factoring and canceling. That one's going to be easily factorable. Okay, and then if we look at the bottom one, that infinity, we wind up getting, if we plug into the top, that negative 5x squared is going to dominate everything else around it. So that's going to go to negative infinity because our leading coefficient is negative. And then on the bottom, we do that and we get infinity. Okay, both of these were what we described as those indeterminate forms. And there's a whole bunch of indeterminate forms that we deal with. And those are listed right here. So 0 over 0. Any combination of infinity over infinity, positive and negative, as you see there. Now, in mathematics, there's more kinds or more different, that sounds really weird, just more versions of what we consider to be indeterminate, and those are listed right here at the bottom. Let me get a different color. So those are listed here. Okay, in Calculus 1 and Calculus 2, AP Calculus BC. We're not really going to deal with those very often. The ones we're going to deal with the most often are these. Okay, and you learned those in a Cal 1 class. You might learn the new indeterminates in a Cal 2 class at the end, or maybe the beginnings of a Cal 3 class. Okay. So we always had processes to figure this out, especially those algebraic processes. But if we look at the next two limits down here, these two, okay, if I plug into the top one, I'm going to get 0. On the bottom, I'm going to get 0. There's no algebraic process to help me kind of break that down. So I would have to resort to graphing of the function, which now we know some kind of ways to at least figure out the shape of the graph, things like that. And then the limit to infinity, again, there's nothing algebraic I can do. Those three rules kind of don't apply here. So the process that we have there or have in place wouldn't even help us with these. So again, we go back to graphing if that's all we knew. If we look at the graphs, let's not do that. If we look at the graphs of these two, as we approach 0, I need a different color. Okay, as we approach 0 on this function, our graph actually approaches that point, coming from the left and coming from the right. So we can see clearly that this is going to be equal to 0. Okay, Now here, limit to positive infinity, that means we're going here. Now since we don't have any more of the graph to kind of make a decision, we'd have to kind of guess or estimate, or as Patrick likes to say, eyeball, where this would actually go. So we don't really have a good process to figure out that limit. Okay, so these limits started to be studied, and the mathematician, his last name is L'Hopital. That's how you pronounce it, L'Hopitals. That's pronounced L'Hopital. He was a German mathematician. So he studied limits, and his rule is how we deal with situations like the ones here, like that, like this one right here and this one right here. Okay, and what L'Hopital said was, let me get to the top, that if we have a limit that is in fact a ratio, like those two were, okay, in that form, and that when we do direct substitution, we get 0 over 0. Okay, so that means the limit of f of x would be 0 on its own, the limit of g of x would be 0 on its own. Or if we get positive, negative infinity as a result of the f of x on its own and the g of x on its own. So if this were to happen, so if these two things occurred, that was terrible. So if these two things were happening, one of those two things, then L'Hopital said that if we look at the limit and we take the derivative of the numerator independently and the derivative of the denominator and reevaluated that limit, that means that our limit of the ratio f of x to g of x would be equal to the limit of the ratio of their derivatives. That kind of helps us a lot with functions that we have to go graphically, because now we kind of have an algebraic way to do that. Okay, so because this is a rule and it has some prerequisites, and those are the things that I showcased in that blue mark that I made up there. Those are some requirements that have to happen in order for us to even be able to apply L'Hopital's rule. So we always want to check those requirements, and we want to check them independently. The notation, as I've said from the beginning, is pretty important, and that can be even, this process justifies why it's so important and the little things that we have to do. And if we want full credit, the processes and the requirements have to be met. So for instance, I know that was a lot. I said a lot. So let's kind of just look at a problem then, and it'll start to make sense. So if I look at B, I know, go ahead and skip over A. I'm going to be skipping around here and there. So I want you just to kind of skip around with me. So if we look at B, if we look at the limit of them independently, because that's the requirements for the use of this rule. So I want to look at the limit. That is terrible. I just don't know how to write today. If I look at the limit as x approaches -3 of my numerator alone, I would see that I would get 0. Okay. Let me look at the denominator. I want to do the same thing, and I want to do these independently because the requirements are about our independence of our numerator to our denominator. So direct substitution. Again, if I plug in, I get 9 minus 5, which is 4. The square root of 4 is 2, and then 2 minus 2 would give me 0. So because of this, I can say by L'Hopital's rule, I can do LH for short. That's an acceptable abbreviation. Because of the fact that my numerator is 0, the limit of my denominator is 0, I can apply this rule. And to apply this rule, we take the limit as we approach that exact same value, and we're going to take the derivative. But we're not taking the derivative of the entire function. We're taking the derivative of our numerator and the derivative of our denominator independently, okay? Because that's what the rule says. So if I take the derivative of my numerator, I'll get 1 as a result. And in my denominator, if I take the derivative, that's at square root. So I'm going to use that rule that's on that pink sheet in front of your journal. And the rule said, derivative are u prime on top over 2 square roots of the original u. Sorry, not the minus 2. to minus 5. And then the derivative of that negative 2 would go to 0. So there's my derivative right there. Okay. So here we have the derivative, and what I'm going to do now is go back and plug into my equation. Okay, go back to my direct substitution. Once my derivative is done, I want to try direct substitution. So 2 over negative 3, or 2 times negative 3, over the square root, 2 square roots of 3 squared minus 5. Okay, so if we think about this, those 2's are really going to cancel each other out, so that's nice. So we wind up getting 1 over negative 3 over, and then if we do that calculation 3 squared minus 5 gives us 4, and then the square root of 4 gives us 2, and dividing fractions, we're multiplying by the reciprocal, so we get negative 2/3. And there is, in fact, my limit. So before, I would have to use something like rationalization, and hopefully that would work out. It would be messy for this problem, but we could do this the long algebraic way. But now that we know a little bit more about derivatives, we can actually do this a lot faster and a lot quicker. Okay, so what I want you to do is to pause the video and then work through A, and when you're done, resume the video. Make sure you pause it. So let's see how we did. If we reveal what we did here, there's my work. Okay, that one was a little bit easier than this one because the derivative was easier. So the first thing I did was, in fact, look and verify that the limit of my numerator was 0 and the limit of my denominator is 0. That is a crucial step. That is, we're looking at the requirements and making sure that we meet the requirements before we actually apply the rule. And then once we did that, that derivative was pretty easy. We got 5. Okay, let's look at another example. Okay, let's look at this one. Okay, you might want to write small, just a little bit of warning. So the first thing I want to do is take the limit as x approaches negative 2 of my numerator. Okay. And I want to verify. So I would get a negative 8. So that would give me negative 8 plus 4 plus 16 minus 12. Did I do that right? Negative 8 plus 4 gives me negative 4, plus 16 gives me 12 minus 12, which gives me 0. Okay, so I did verify that. I also want to verify my numerator and my denominator independently. So this kind of gives us a better way to start the idea of plugging in to see if we get 0 over 0, because I know that whole idea of setting it equal to 0 over 0 was kind of confusing to some people. Okay, so this kind of eliminates that fact. We're looking at them independently to see if they meet that requirement. So again, negative 8, that would give me positive 32 minus 40 plus 16. And that, as of course, results in 0, which means by L'Hopital's rule, I can actually take the limit as x approaches negative 2 of the derivative. So 3x squared plus 2x minus 8 over 3x squared plus 16x plus 20. Okay. So now if we think about plugging in, and I want to just verify to make sure the plug-in is going to work, so I'm just going to do some mental math. So if I plug into my numerator, I get 12 minus 4, which is 8, 8 minus 8, which is 0. Okay, so I want to verify that in my denominator as well. So that would give me 12 minus 32 plus 20. Again, that would give me 0. Which means I get 0 over 0. So I can actually apply L'Hopital's rule again. So I'm going to change colors. I can keep applying L'Hopital's rule over and over and over again as long as I get 0 over 0. I want to show that this is in fact 0 over 0 again, so I'm using a different color for my next step. So negative 2, 3x squared plus 2x minus 8, that gives me 0. Okay. I already verified it, I did that mental math. So I do 3x squared plus 16x plus 20 is also equal to 0. So again, I can say by L'Hopital's rule, this is also equal to the limit as x approaches negative 2, and I can take the derivative again. So 6x plus 2 over 6x plus 16. And then I can see this was definitely something that I'm not going to get 0 over 0. So 6 times negative 2 gives me negative 12 plus 2 over negative 12 plus 16. So I'll wind up getting, what's that, negative 10 over 4 or negative 5 over 2. Okay, and that's cool because if we go back to the original function, we wouldn't know how to factor that. It would be complicated to factor if it's even factorable. We'd probably have to use something like long division, and nobody wants to do that. So L'Hopital's rule kind of clears it up. So again, what I want you to do is to pause the video and work out D, and then come back and see if you got it right. I'm serious, pause the video. Okay, let's look at that and see if we got it correct. So there's my work for D. This only had to be done once. Doing it once worked. I'm done. I got a number. I don't have that 0 over 0, so I'm ready to go. Okay, it is really important that we never say equal to 0 over 0. Remember I said highlight this. Okay, because those are not numerical values, so we can't say that it's an equal to a value. And I discussed this when we did limits at the beginning. But by splitting it up and looking at your numerator first and looking at your denominator second, I can prove that 0 over 0 just through that calculation alone. So it kind of helps a little bit. Okay, let's look at a couple more problems. Okay, so going back to the one we started with in A, that was kind of the graph that we saw, and we kind of had to make, you know, a decision. We couldn't really see, we didn't really want to know, but L'Hopital's rule will lead me to whatever that value is. So I'm just going to do L'Hopital's rule and see if it works out. So if I plug into my numerator, cosine of 0 would give me 0, and I'm sorry, cosine of 0 is 1, and 1 minus 1 give me 0. And then the limit as x approaches 0 of x squared minus x, and that will give me 0 again. So then I can say by L'Hopital's rule equals derivative of cosine of x gives us negative sine of x. Oh, sorry, a limit. I almost made that a terrible mistake by dropping my limit. I don't want to do that. Okay, I get negative sine of x. The derivative of 1 goes to 0, or negative 1 goes to 0, and I get 2x minus 1. Okay. So if I go back to plug in, and I want to do this mentally to make sure I don't have to apply L'Hopital's rule again, negative sine of 0, well, that's 0. I just need to hope that my denominator is not 0. If I plug into that, I get negative 1. And 0 over negative 1 is okay because we know that to be 0. So try the next problem, B, pause the video, try it, and then come back. Okay, let's see how you did. Okay, this one we had to use L'Hopital's rule twice. And because the limit, remember the natural log of 1 is 0, okay, here you do have to keep in mind that this e right here is not the function e, it's the number e. So it doesn't have an x exponent, so we just treat it like a 4, like a 5. So the derivative of ex would just give us e. So we had to apply it twice, and I got this from my pink card as a shortcut to the derivative of this. This is on our pink cards. So now we're starting to see why those shortcuts are really beneficial, because they can get to the problem faster. Okay, let's look at this example. So infinity. Now, I can't use my 3 rules here. If I plug into my numerator, that 4x squared is going to take over because it's our largest term. So it's going to go to infinity because it's quadratic, and that's where quadratics go. And then our bottom functions, e to the 5x goes to infinity, and natural log of x goes to infinity as well, if we think about their graphs. So I can use L'Hopital's. I want to show first that it's meeting the requirement. So the limit as x goes to infinity of 4x squared minus 5x plus 2, that gives me infinity. The limit as x goes to infinity of e to the 5x plus the natural log of x also goes to infinity. Okay, which means by L'Hopital's rule. By L'Hopital's rule. I always want to say that. This is equal to the limit as x approaches infinity of 8x minus 5 over 5e to the 5x, again off my pink card, plus 1 over x. Okay. So my numerator is still going to go to infinity. My denominator, a piece of it, that 5e to the 5x is going to go to infinity. That 1 over x is actually going to go to 0, but it's still infinity plus 0. Okay. So that means I have to use L'Hopital's rule again. So I'm just going to change colors. So I want to show that the limit as x goes to infinity of 8x minus 5 is equal to infinity as well. And the limit as x goes to infinity of 5e to the 5x plus 1 over x is also infinity. So then I can say by L'Hopital's rule, I want to say that every single time, the limit as x goes to infinity of 8 over 25e to the 5x minus 1 over x squared. Okay, so 8 is just 8, but everything that's causing our problem, our 25e to the 5x, that's going to infinity. So I have 8 over infinity, 8 over a really large number, which means I have a very, very small number. So this actually goes to 0. Okay, try C on your own, and then pause the video and come back to it. So the answer for that one, let me move the box. There we go. Was just negative 5/3. I didn't have to use L'Hopital's rule. I could have. It would have worked out. I would have gotten negative 5/3. I would have had to use L'Hopital's rule twice. But if I know the 3 rules are faster, I'm going to go to the faster method every single time. So if me knowing that and getting there really quickly, I mean, I can do that. I have that ability to just jump there. Okay, so if you did L'Hopital's rule, you would have gotten the same thing. But you really didn't need to do L'Hopital's rule there. Okay, so let's look at the bottom 2. Okay, so here we have a graph, and we want to find the limit of not this graph as we approach 3, but the limit of f of x over x squared minus 9. So if we look at this graph, as we approach 3, our f of x is actually approaching 0. Okay, because that's the graph of f. So I already know that the limit as x approaches 3 of f of x is equal to 0. That's where that graph is from. And the limit as x approaches 3 of x squared minus 9, well, that's just 3 squared minus 9, which is 0. So again, I have 0. So I can say by L'Hopital's rule, you see how I'm doing that every single time? I'm doing my process the same every single time. So L'Hopital said that we can take the derivative of our numerator independently and the derivative of our denominator independently, and then just evaluate the limit at the same value. So if we think about f prime of x, remember f prime is the derivative of f. So we're looking for f prime of 3. So we're looking for the derivative or the slope at that point. And that point is on a line, so we can use our rise over a run. So up to left 1, so rise is 2, Run is -1, so we get -2. Over 2 times 3, which is 6, so -1/3. Okay. So what I want you to do is to try B on your own. I'm not going to give you the answer to that. We'll kind of discuss that when I'm back in class on Thursday. If you have any questions, come see me. I will not be available for tutoring after school Wednesday, but we can discuss any problems in class and then after school on Thursday. Okay, if you need anything, just send me a message.